What's the best way to deal with problems? Anticipate them and prevent them from happening in the first place. When's the most likely time to have an unexpected problem, especially when you're an engineer? When designs change. Here's a design change I'm concerned about. Here we have a picture of an older airplane. Here we have a picture of a newer one. Notice anything different about the engines? The newer ones are bigger. They're bigger and they're more efficient, which is fantastic. But because of some particular work I've done, I have some concerns about them. I'm concerned about these really tall blades here. Not when under normal flying, when everything's great, but under two specific conditions. When a plane goes like this, that's called yaw, or when a plane goes like this, that's called pitch. Here, let me show you, I got a couple of good YouTube videos you can watch to see that actually happening. Sometimes things get a little rough. You see, this big rotating wheel of blades is a gyroscope. And when a plane goes like this or this, gyroscopic forces appear that aren't normally there. Let me show those to you. So when a plane experiences yaw, these are the gyroscopic forces on the blades. Now you might think this pattern is well known, but it's not. The gyroscopic effect has been a very difficult thing to figure out for a very long time. And I only posted this information about a month ago in my video, The Truth About Gyroscopes. See, in universities all over the world, the gyroscopic effect is taught using what's called the conservation of angular momentum. The conservation of angular momentum would only give you the average of these forces, not these gyroscopic forces, not this exact pattern. In the situation with these blades, you'd want to know what each blade is experiencing as it rotates. More importantly, you want to know the maximum force the blade experiences right here, not the average force. Using the conservation of angular momentum method, you would underestimate this maximum by 29.3%. And that 29.3% means a lot more out here than it does here. These gyroscopic forces won't have to be underestimated anymore, thanks to this equation. This is the right equation. The right equation can map out the gyroscopic acceleration of each of these blades all along the blade at any point in time. Consider this blade right here. Just consider the last 2-inch section. Well, that last 2-inch section has a mass. The center of its mass would be somewhere in the middle of the 2-inch section. So this R here would be the distance from the center of the wheel to the center of that section's mass. And using the right equation, you could calculate the acceleration that mass is experiencing and come up with the gyroscopic force from that. You repeat that process for each section along the blade, add them all up, and you would get the total gyroscopic force experienced at the blade's attachment point, the blade root. You repeat that process for each section of the blade, add up all the forces, and you'd have the total gyroscopic force experienced by the blade root right there. Easy peasy now. All you need to know are the distances involved, how fast the blades are spinning, how fast the plane was rotating, and the mass of the blade, mass distribution of the blade. An engineer who knows Python language could write a program to calculate all this precisely in what, like 2 days, even if he takes long lunches. Now let's talk about cyclic fatigue. So when a plane rotates like this, these gyroscopic forces are present. So let's say a plane rotates for 1 second and that engine's speed is 600 RPMs during a rough landing. So imagine what each blade would experience as it goes around. Each blade would experience 2 pulls. Nothing when it's here, a forward pull this way when it's here, nothing once it gets over here, a backwards pull when it gets over here, and finally nothing here. That's in one rotation. It would experience 2 pulls, forward and back. That's called a force cycle. But during the 1 second the plane is rotating, each blade will go around 10 times. So each blade would experience 10 force cycles. Any material can develop cyclic fatigue. It depends on the type of material involved, how many cycles were experienced, and how strong were the forces during the experience. Cyclic fatigue would first show up as microscopic cracking in the material surface. In this blade's case, most likely here at the blade root. But how do you keep track of all these cycles and what the engines experience? I mean, sometimes the weather's good, sometimes the weather's bad. Sometimes there's crosswinds, sometimes there's not. There's turbulence, there's not. Well, fortunately, these planes are already equipped to track and monitor this. In my research, trying to figure out the gyroscopic effect, I learned about ring laser gyroscopes, and these planes have them. Matter of fact, they have 3, and they monitor when the plane experiences yaw, when a plane experiences pitch, and when a plane does this. Now that's called roll. Roll will not create any gyroscopic forces, only yaw and pitch. Plus, these planes have computers. And they can always be monitoring for severe rotation. When they detect one, they can bump up a counter. And that counter would go with the engine and tell you what that engine has experienced. The last thing I want to mention is harmonics. As you've seen, these gyroscopic forces are cyclic. And the frequency they occur depends on the engine speed when they're present. Now, something like a structure like this blade has what's called a natural harmonic frequency. And if the gyroscopic frequency gets close to that natural harmonic, then these gyroscopic forces would become additive, meaning they would build up quickly. This blade is probably pretty stiff, probably pretty tough. I imagine it would have a very high harmonic frequency. The engine manufacturer should know this. Well, I've done a lot of talking, so now let me do some demonstrations. This is a gyroscope I built while I tried to figure out the gyroscopic effect. The wheel is made of A36 steel, pretty tough stuff. It weighs about 6 pounds and it's turning just under 1,000 RPMs. The assembly the wheel is mounted to is balanced for weight. This pivot point goes right through this assembly's center of gravity. So the only thing making this unbalanced right now is this little bar. So let me give this a little turn and you can watch the gyroscope pick up the bar. So the forces were there while I was turning. When I stop, the forces disappear and the weight of the bar put the gyroscope back down. So now let's add a little weight. This is about 1 pound. Remember, the wheel is 6 pounds. So I'll give it another little turn and you can see the gyroscope pick up the 1 pound weight from about 9 inches away. Now let's go big and we'll add a 3 pound weight. This would be 50% of the wheel's weight. Now I could turn it slowly and the wheel won't pick up the weight. The forces are there, but they're not large enough to pick up the weight. So it's not how much it moves, it's how fast. So I'm going to rotate it a little more quickly now. You saw the gyroscope pick up the weight. But can a plane rotate that fast? I don't know. I've been on some turbulent flights. Turbulence seems to happen pretty fast. But in turbulence, does the plane go straight up and down like that? That wouldn't cause any gyroscopic forces. Or does a plane do it like that? Now that would cause some gyroscopic forces. I did notify the FAA about all this using their website hotline. Here's what I wrote them. And they did respond, and here's their response with the case number. Now, I didn't do this flippantly. I spent a lot of time looking through their public website for anything I could find about how gyroscopic forces affect airplanes. And I did find a lot of stuff. but it was all about flight controls, how it affects the engine shafts and the engine bearings. I saw an extensive paper on rotor dynamics. It was very impressive. But I couldn't find anything about how gyroscopic forces affect these blades individually, or the possibility of how it could cause cyclic fatigue. And maybe it was there, but I couldn't find it. And when there's an unknown, I just always, when it comes to safety, I always err on the side of caution. My loved ones fly, your loved ones fly. When it comes to these engines, I don't think you can be too safe. Thank you for watching.